Hey, College Math. Here is section 4.3. We have doubling time and half-life as the idea for this section, okay? Not too much of a demanding section. Our only objective is to write and use these two models. So we're gonna kind of write them down right now and see what they are. And then we're just gonna use them in a couple different problems. Not too much different from what we've been doing so far. Okay, the doubling time and half-life models are actually just special cases of the exponential growth model that we've been working with so far. Okay, so starting with double time, or not double time, doubling time. Okay, let's go ahead and start by writing that equation. Sorry, I dropped my writing tablet, had to pick it up. We have doubling time. Okay, and doubling time, it's it's in the name. It's the amount of time it takes to double. And most often in the problem, it'll tell you exactly, the time it takes to double is this much, or this population doubles in so and so time, right? And so if y equals y naught, we still have the same two variables there as our exponential growth model. But now instead, here it's going to be a predetermined 2 instead of 1 plus r. T to the power of t divided by t. Okay, so y and y naught, same thing from the exponential growth model. Here, if we're doubling, our growth rate, our r, is 100% because that's how much we're growing by every single time when we double. When something doubles, goes from 2 to 4, it gets multiplied by, or we add 100% of itself back into it, right? If I start with 2, 100% of 2, and if I add 2 into that, I get 4. And you continue that process, right? The thing that's different is the exponent, right? So t is most often time, right? With doubling time and half-life, our variable up there is almost always just time, right? So t stands for time, and then d stands for the doubling time. Okay, the amount of time it takes for the quantity to double. Okay, and we'll most often be given d. Sometimes we're solving for t, sometimes we're solving for y naught, sometimes we're solving for y. It depends on the situation, right? And then we have, our half-life model. Okay, and half-life is very similar to doubling time. It's the amount of time it takes for a quantity to go from its original amount to half of where it started, right? So the amount of time it would take for me to go from, say, 100 to 50, right? Or from 20 to 10, right? The amount of time it takes for it to go from wherever it started to exactly half of that amount, okay? So the model for this one also pretty similar, y equals y naught. Okay, it's got ahead of myself. It's 0.5 inside the parentheses to the power of t divided by capital H. Okay, and so this is half-life, and we're trying to figure out how much time it takes to go from its original amount to 50% of that original amount. So we're decaying, we're decreasing, and so it's going to be 1 minus 0.5 because we're decreasing by 50% every single time. And so 1 minus 0.5 is 0.5. And so that's why that's the number inside. T is still time, but then now H is the half-life of the thing that you're looking at, whether it's a substance or a population of animals or bacteria, whatever the case might be, right? But these are your two models. They're fairly the same. The really only super mega differences are the 2 and the 0.5 and the D versus the H, okay? So let's just go ahead and do some examples. Our first one is a water tank is found to be contaminated with a colony of 80,000 E. coli bacteria. This colony doubles every 5 days. Okay, so how large is the colony after 2 weeks? Let's start there. And actually, before we start there, let's start by writing out our equation, okay? We're doubling every 5 days, so this automatically tells us that we're working with the doubling time model, okay? So the model I'm using is y is equal to y naught times 2 to the power of t over d, okay? So let's fill in some of the information we know. We know that it starts off with 80,000 bacteria, so that's our initial amount, our y naught, times 2 to the power of t. T is most often going to be the variable that we leave alone, that we're going to be able to plug stuff into. And it doubles every 5 days. That's our D, okay? So here's our equation, 80,000 times 2 to the power of t over 5. Okay, so for the first question, how large is the colony after 2 weeks? Okay, mind your units, right? Your units should always match up with the doubling time. So if my doubling time is in days, then whatever I plug in for t needs to be days. So maybe even writing yourself a note will help you. In this case, it's the number of days, and you always know that by looking at the units that are in your doubling time, okay? In this case, it's days, so t should be in days. So if I'm looking at 2 weeks, how many days is that? That is 14. So I need to plug in 14 for t. So 80,000 times 2 to the power of 14 over 5, okay? And then from there, it's just putting it into your calculator. So I'll go ahead and give you a second to do that. Okay, you can do this in your own calculator, in Desmos, whatever you have available to you, right? So what do we get when we do this? Let's see. We have 2 to the power of 14 divided by 5. Okay, and then that times 80,000. That's going to give us 557. I'm going to change these to approximation symbols because we're going to have to round up since we're dealing with living things. 557,152, just kidding, not 52, 53. Oh, I didn't even have to worry about it. I thought I already wrote the 2 out. I was like, I have to change that, but I didn't. Yep, 557,153 bacteria. Okay, there's our answer. So just like the 4.2 chapter here, it's just a matter of plugging in the number, right? And this number we should always check to make sure the numbers make sense, right? 14 days, that is 2 doubling periods. So this bacteria has had time to double twice, right? So if I double 80,000, so multiply that by 2, that's going to be 160,000. And if I multiply that by 2, that's going to be 320,000. Okay, so it's pretty close. And if I double it one more time, our answer should be between 320,000 and what I'm about to get from multiplying by 2, which is 640,000. And it is 557,000, right? And so we're kind of right in the ballpark. That should be where we are, right? Cool, so that worked out. Now, the next question is, how long will it take for the colony to grow to 90,000 bacteria? Okay, so this is a different question. How long will it take for it to grow to a certain amount of bacteria? How long, meaning we're solving for t. So this is our ending amount. We still use the same starting amount. So I go 90,000 equals 80,000 times 2 to the power of t over 5. Okay, so I know everything except t. Well, it looks like I'm solving for the exponent. Okay, if you remember back from our algebra review chapter for chapter F, we're going to need to use a logarithm here in order to get that exponent down. Okay, but before we do that, we're going to need to divide over this 80,000 because I want to get this exponential piece by itself. So divide both sides by 80,000. Okay, and so what do we end up getting from that? That's going to be 1.125 is equal to 2 to the power of t over 5. Okay, here's where I need to take the logarithm of both sides, which will allow me to bring down this entire exponent, okay? So I'm going to take the log of both sides, log base 10. Log of 1.125 is equal to log of 2 to the t over 5 power. This exponent ends up coming down. So I end up with, I'm going to flip the equal sign so I can have my equation, my variable on the left-hand side. T over 5 log of 2 is equal to log of 1.125. Okay, so the first thing I want to do here is divide over the log of 2. That's not that we're used to that, right? We're used to just immediately doing that. Divide over log of 2. So I get t over 5 is equal to log 1.125 over log of 2. And then my last step is to multiply that 5 over to each side, right? And that's 5 over 1, so it's going to be in the numerator. So my overall answer, my exact answer is 5 log of 1.125 over log of 2. And then from here, it's just a matter of putting it into our calculator. Let me go ahead and switch over to Desmos to show you how we would do that in this case, right? That way we can just kind of put it all in one single line. So I'm switching over right now. So then I click on my first entry box, pull up my calculator, or my keyboard, sorry. Start with the division symbol so you can get the fraction. 5, go to functions and then miscellaneous, log. And that top log was 1.125. Oops, it took me out of the, there we go, that's where I want to be. 1.125, close, and then press onto the denominator, log of 2, parentheses. Okay. And so there is our answer, 0.849. And in that case, it actually makes this round up to 0.85 because of the 6 right here, since we're doing 3 decimal places, right? So 0.85 is our answer here. Okay, heading back to the whiteboard, 0.85. And that makes sense, right? In 5 days, it doubles to 160,000. We're talking about 90,000 right here, which is way less than the 160,000, right? It's between 80,000 and 160,000. So we know that our amount of time should be between 0 and 5 days. We're cutting it to a little bit under 1 day because we got an answer of about 0.85 days. Okay, so our answer is a little bit less than a day. Okay, awesome. And so there is the doubling time example. Now let's do an example using the half-life. Example 2, so lead-209 is a radioactive isotope that has a half-life of 3.3 hours, okay, making note of our units for our half-life in this case, because it'll be the same thing, same idea where our T should match up the units of the half-life. Suppose 40 milligrams of the isotope was created in an experiment, okay? Starting question is how much of the isotope remains after 14 hours? So let's find our model first. Okay, we're using the half-life model, so y equals y naught times 0.5 to the t over h power. Okay, our initial amount is 40 milligrams times 0.5 to the t over 3.3, since that's our half-life. Okay, our units do match, so I can immediately just plug in 14. So 40 times 0.5 to the 14 over 3.3. Okay, and the nice thing about Desmos is you can, just like we did with that log over log stuff, you can just put this in one little box in one single line, and it'll just calculate it immediately for you, right? Instead of doing it in parts. So I'm gonna do that really quick. I'm gonna head over to Desmos. And so we have 40, left parentheses, 0.5, right parentheses, a to the b, 14 divided by 3.3. Okay, and that is exactly what we have in our setup. And so here's our answer, 2.113. Okay, 2.113 milligrams will be remaining. Head back. So we have approximately 2.113 milligrams. And so here with this question, milligrams, that is a continuous variable. Something is allowed to weigh, half a milligram of 0.03 of a milligram. So in this case, I don't really need to round up to a whole number. I can just round to my 3 decimal places like we're used to, right? Remember, the only time we need to round up to a whole number is if we have some kind of living object or living thing, like a person, an animal, bacteria, whatever the case may be, or for objects that it wouldn't really make sense to have half of, right? Like a desk. All right, so there's the answer for that. And then how long will it take for the isotope to decay to 1 milligram? Same thing as the other question. We set this equal 40, 0.5 to the t over 3.3, since it's asking how long, is equal to 1 milligram. Okay, we'll need to divide over the 40 because we want to isolate this. So divide both sides by 40. We get 0.5 to the t over 3.3 is equal to 1 over 40. And I'm wanting to know if that's a nice decimal or not. I don't know off the top of my head. Let's see. Yeah, it's okay. It's 0.025. Okay. And then here, just like we did last time, we're taking the log of both sides. So we get log of 0.5 to the t over 3.3 is equal to log of 0.025. And then now we can bring down this exponent to the front. We get t over 3.3 log of 0.5 is equal to log, same thing, right? 0.025. Cool. So then first thing, we divide over that log 0.5. So I get t over 3.3 is equal to log 0.025 over log 0.5. And the last step is to multiply that 3.3 over. So I get t is equal to 3.3 log 0.025 over log 0.5. Let's punch this into decimals really quick. Okay. So next box, do my little fraction. 3.3 functions log 0.025, right parentheses, press into this bottom one, log of 0.5. Okay, I'm a little paranoid that I did that in the wrong order. Let me check really quick. Nope, that's right. Okay. So here's our answer, 17.562. Okay, so our t is equal to about 17.562. What's our units? Hours. Okay. Awesome. So there is 4.3, you guys, doubling time and half-life. Hopefully this sounds good. I will see you in the next video in section 4.4. Okay. Have a good rest of your day.